Hello, welcome to your quiet place in history. I am your geneticist, and tonight we invite you to drift off to over 2 hours of profound historical and scientific discovery. In the world of power, crowns, and conquest, there is one constant silent architect: the gene. For centuries, the health of monarchs has determined the fate of nations. Tonight, we gently open the historical records and the microscopic world of DNA to understand the real stories behind the royal diseases, the genetic secrets that shaped the mightiest figures who ever lived. This is your comprehensive collection of Decoding Dynasty, presented with soothing white noise to guide you toward a deeper understanding or a deeper sleep. Relax, breathe, and let the historical mysteries and the quiet hum of science begin. Tonight, we will first delve into the King's Crimson Code story, Henry VIII and the shadow of his genes. The court of Henry VIII, a tapestry of power, passion, and tragedy. We will delve into the enigma of Henry VIII, a monarch whose reign was as turbulent as his personal life. Behind the opulent facade, a silent, invisible force was at work, a genetic legacy that would twist a king's destiny and shape the fate of a dynasty. We know the stories of his 6 wives, the political machinations, and the brutal executions. But what if the true story lies hidden within the very architecture of his DNA? A story of a hidden genetic code, a crimson code, if you will, that could have shaped his destiny. For centuries, historians have grappled with the enigma of Henry VIII, and the question lingered: why the string of tragic miscarriages, the stillbirths, the king's descent into paranoia and brutality? Why did the dramatic shift from a vibrant, athletic king to a paranoid, tyrannical ruler happen? Historians painted portraits of political stress, of syphilis, of mere chance. But what if the answer lay not in the grand halls of power, but in the microscopic realm of molecular genetics? Recent suggests a chilling possibility. Henry VIII may have been a carrier of the Kell blood group, and possibly a victim of the rare X-linked disorder McLeod syndrome. Let's dissect this. You're familiar with the ABO blood typing, but the Kell system is a more subtle yet potent player. At its core, it's a matter of proteins, Kell and XK linked by a sulfide bond residing on the surface of red blood cells. Think of it as a molecular handshake, a delicate dance of proteins. If Henry carried the Kell antigen and his wives Catherine and Anne did not, a dangerous immunological clash could have occurred during a first pregnancy with a Kell-positive fetus. The mother's body, recognizing the Kell antigen as foreign, would produce antibodies. In subsequent pregnancies, these antibodies could attack the fetus, leading to miscarriages and infant deaths. This is not just a historical footnote, it's a molecular drama playing out at the cellular level. But the story deepens as Henry aged, his behavior shifted dramatically. The robust athlete morphed into a paranoid tyrant. This brings us to McLeod syndrome, a rare X-linked disorder intimately linked to the Kell system. The culprit? The XK gene. This gene encodes the XK protein, a crucial partner to the kelp protein. In McLeod syndrome, mutations, deletions, insertions, even single nucleotide substitutions disrupt this partnership. The result, the XK protein, is either absent or dysfunctional. This disruption leads to a cascade of neurological and muscular problems: chorea, cognitive decline, psychiatric disturbances, a molecular storm wreaking havoc on the nervous system. Imagine the intricate network of neurons, the delicate signaling pathways, all thrown into disarray by a single genetic flaw. Now consider the XL nature of McLeod syndrome. Males with only one X chromosome are particularly vulnerable. If Henry inherited the mutated XK gene from his maternal lineage, possibly from his great-grandmother, Jacquetta Woodville, he would have expressed the disorder. This is not just a theory. It's a reflection of the fundamental rules of X-linked inheritance. Imagine a genetic thread passed down through generations, shaping not just a king's personality, but the course of a nation. At the molecular level, we're talking about the absence of the KX antigen, which leads to acanthocytosis, abnormally shaped red blood cells. These cells, along with the progressive neurological damage, painted the portrait of Henry's decline. Think of it as a microscopic rebellion, a cellular revolt against the blueprint of life. The tale of Henry VIII, once confined to the realm of politics and personality, now resonates with the echoes of molecular genetics. This is not just a historical puzzle. It's a testament to the power of our genes, the silent architects of our destinies. It's a story of how a genetic legacy, hidden within the very fabric of our being, can shape not only an individual's destiny, but the course of an entire era. It's a reminder that even the most powerful figures in history are subject to the intricate, often unforgiving laws of biology. And it compels us to ask, how much of our own stories are written in the crimson code of our DNA? And how much of our own lives are shaped by the silent whispers of our genes? Decoding Dynasty is the only place where we dig through history's DNA like it's the world's most complicated Ancestry.com result. Now, we're diving headfirst, pun absolutely intended. You'll see why, into the fascinating and frankly somewhat soggy story of Emperor Ferdinand I of Austria. Picture this: you're the top dog of a massive empire, but your head's a little, shall we say, roomy on the inside, thanks to something called hydrocephalus. And to top it off, your brain throws more surprise parties, aka seizures, than a toddler with a drum set. Born into the Habsburgs, a family tree so intertwined, you practically needed a genetic map just to figure out who was related to whom. Spoiler alert, everyone was. Ferdinand inherited the throne in 1835 and also became the top monarch in Hungary and Bohemia. Now history paints him as, well, history isn't always kind, and Ferdinand's reign is often painted with the broad brush of indecisive and not exactly a political powerhouse. Some even nicknamed him Ferdinand the Good-Natured, which in royal circles can sometimes be code for a bit out to lunch. But was he truly simple-minded? Or was there more to the man whose head was, shall we say, carrying a little extra brain beverage due to hydrocephalus? And that's just the beginning of our medical mystery. Poor Ferdinand also had epilepsy that threw more surprise parties in his brain than a confetti factory on overdrive. We're talking up to 20 seizures a day. Imagine trying to run an empire when your own neurological system is staging a daily revolt. You'd probably need a really good nap or, to abdicate, which he eventually did amidst the chaos of 1848. So what's the genetic tea here? Well, Ferdinand's parents were first cousins. Yes, you heard that right. Actually, his parents were double first cousins, which, in the genetic lottery, is like buying all the tickets for the rare and slightly inconvenient health conditions draw. So, was Ferdinand's less than stellar reign down to bad luck, or did his family's penchant for keeping it all in the family genetically load the dice? Their family get-togethers must have been genetically cozy. This level of consanguinity significantly ups the odds of recessive genetic quirks popping up, kind of like finding unexpected treasures, or in Ferdinand's case, unexpected health challenges in the family attic. And in this episode of Decoding Dynasty, we will delve deeper into the medical conditions of hydrocephalus and the electrifying chaos of epilepsy through the lens of modern science. We'll try to piece together if the Habsburgs' fondness for marrying within the family might explain Ferdinand's unique set of challenges. Get ready for a historical autopsy with a genetic twist. All right, so Emperor Ferdinand was dealing with a double whammy: hydrocephalus and epilepsy. Now, these two might sound like they're in the same brainy ballpark, but they're actually playing different games, even if they sometimes share the field. Let's break down what's similar, what's different, and where things get a little complicated. What's kind of the same-ish? Brain stuff. Bottom line, both hydrocephalus and epilepsy are brain-related. They're not like a tummy ache or a bad hair day. They mess with the control center, and both can seriously impact someone's life. Brain acting weird. Both conditions can lead to some not-so-normal brain behavior. Hydrocephalus can cause seizures. Yep, epilepsy's main gig, plus things like delays and trouble moving. Epilepsy is all about those surprise brain misfires we call seizures. Early brain development issues. If either of these kicks in early in life, it can throw a wrench in how the brain grows and learns. Sometimes they hang out together. Interestingly, in some really tough genetic conditions that mess with brain development big time, you can see both hydrocephalus and epilepsy showing up. It's like some genetic mutations are just extra chaotic and cause all sorts of problems. Brain structure gone wrong. Sometimes if the brain doesn't form quite right in the first place, it can set the stage for both hydrocephalus and epilepsy. So, a bumpy start can lead to a bumpy brain experience later on, where they go their separate ways. The plumbing versus the wiring. Think of it this way. Hydrocephalus is more of a plumbing problem. It's about the fluid in your brain, cerebral spinal fluid or CSF, not flowing or draining properly, causing backup and pressure. Epilepsy, on the other hand, is more like an electrical wiring issue. It's about the brain cells firing off in a haywire way, causing those seizures. Different genetic players. While there are a few rare genetic overlaps, mostly hydrocephalus and epilepsy have their own sets of bad guy genes. Hydrocephalus genes tend to be about brain development, cell signals, and these little hairy things called cilia that help move fluid. Epilepsy genes are often about how brain cells get excited or calm down, things like ion channels and how signals get passed between neurons. Different brain roadmaps gone wrong. Developmentally, hydrocephalus is usually about the brain's fluid system not forming or working right. Epilepsy is more about how the brain cells organize themselves, connect, and fire signals where they bump into each other. Seizures, the uninvited guest in hydrocephalus. Here's a twist. Sometimes if you've got hydrocephalus, all that extra fluid and pressure can irritate the brain and cause seizures. So epilepsy can be a side effect of hydrocephalus. The something's really wrong scenario. When you see both hydrocephalus and epilepsy together, it often points to a more severe underlying genetic or developmental issue that's really throwing the brain for a loop. Shunt surprises. And get this, sometimes the surgery to fix hydrocephalus, putting in a shunt to drain the fluid, has been linked to more seizures in some people. It's still a bit of a medical head-scratcher why that happens. Wrapping up this brain teaser. So while hydrocephalus and epilepsy can be buddies in some tough situations, they're generally caused by different things going wrong in the brain. One's a fluid flow problem, the other's an electrical storm. Understanding this helps us get a better picture of what Emperor Ferdinand I might have been up against. So, what did it actually look like for Emperor Ferdinand I, and how do we even begin to understand it now? Back in Ferdinand's day, watching someone have an epileptic seizure must have been incredibly frightening and baffling. People often attributed them to all sorts of things, divine punishment, evil spirits, you name it. For Ferdinand, we know he suffered from severe epileptic seizures starting in childhood. These weren't just little flickers. Historical accounts suggest he had frequent, powerful grand mal seizures, where he'd lose consciousness, convulse, and afterwards he'd often be totally exhausted and confused, a state we now call the postictal phase. Imagine trying to rule an empire with that hanging over your head. Just like epilepsy, the story of hydrocephalus often has roots in our genes. Although the specific players and pathways can be quite different, the genetic landscape of hydrocephalus is complex to say the least. Scientists have linked over 100 different genes to this condition, highlighting just how many different things can go wrong in our genetic code to disrupt the delicate balance of fluid in the brain. Hydrocephalus at its core is all about an abnormal buildup of that vital brain juice, cerebral spinal fluid or CSF, in the brain's ventricles, those interconnected spaces within our brain. This excess fluid causes these ventricles to enlarge, and that increased volume can put pressure on the surrounding brain tissue, leading to a range of neurological symptoms. The way hydrocephalus shows up can be quite different depending on when it develops, whether it's congenital, meaning present at or around birth, or acquired, developing later in life due to things like infections, bleeding, head injuries, or inflammation. As we reflect on the life of Emperor Ferdinand I of Austria, who history tells us suffered from both of these conditions, our modern understanding offers a new perspective. The close genetic ties within the Habsburg dynasty, exemplified by his parents being double first cousins, likely amplified the risk of inheriting recessive genetic factors that could have contributed to his hydrocephalus and severe epilepsy. While we can't definitively pinpoint specific gene mutations without his genetic information, our scientific knowledge illuminates the potential biological realities behind his documented health struggles. Ferdinand's story serves as a poignant reminder that historical figures were not immune to the biological forces that shape our lives. His reign, often characterized as weak and indecisive, was undoubtedly impacted by the relentless burden of his neurological conditions. By examining his life through the lens of genetics and modern medicine, we gain a deeper appreciation for the personal challenges he faced, amidst the backdrop of a powerful empire. Tonight, we are looking at the most tangled family tree in European history. And let me tell you, it makes your holiday dinner awkward look like a picnic. We're talking about Charles II of Spain, the very last of the Spanish Habsburgs, who gained the rather dramatic nickname, the Bewitched. Now, why the Bewitched, you ask? Well, imagine being born into one of the most powerful dynasties in Europe, destined to rule a vast empire, but from day one, you're, let's just say, not quite right. Whispers followed him everywhere about his health, his rather unique looks, Habsburg jaw, oh, we're getting into it, and most importantly, his terrifying inability to produce an heir. The whole kingdom thought he was under a literal spell. But here on Decoding Dynasty, we're armed with 21st century science, not fairy dust. Forget witches and warlocks. The real magic trick was how many times cousins married cousins in that Habsburg family. His family tree didn't just branch. It actually braided itself into a genetically problematic pretzel, which, spoiler alert, did not end well. We're going beyond the palace rumors and historical gossip to use the power of genetics to understand why Charles was so incredibly unwell. We're going to unravel a tangled web of ailments, from his struggles with walking and talking to the intense questions surrounding his very sex and ability to father children, all the way to the organ failures that ultimately claimed his life. And trust me, when you see just how much inbreeding went on, bewitched starts to sound like the least wild explanation. So, grab your comfiest chair and your biggest magnifying glass because we're about to journey back to the Spanish court to decode the real story of the bewitched king and discover the fascinating, sometimes darkly humorous, genetic truths behind his legendary infirmity. So, after that rather uncomfortable family reunion discussion, let's actually meet the man himself, King Charles II of Spain. He was born in 1661, and right from the get-go, things were complicated. His dad, Philip IV, was pretty old for the time, 56, and Charles's older brother had just passed away, so the whole court was desperate for a healthy heir. When little Charles arrived, there was initial joy with reports calling him a robust male, which, spoiler alert, was probably a bit of hopeful spin doctoring. Because almost immediately, whispers flew around Europe, including from his own Austrian relatives saying, we don't think Spain actually has a prince because he's not male, but female. Talk about a rough start to life. Now let's talk about his looks. When you see portraits of Charles II painted by masters like Claudio Coelho, you immediately notice that infamous Habsburg jaw, that severe prognathism where the lower jaw juts out. It wasn't just a facial quirk. It was so pronounced that he had trouble chewing, leading to poor eating habits and even a legendary addiction to chocolate. Beyond that, we see descriptions of a long face, prominent chin and ears, widely spaced, and sometimes even a prematurely aged appearance. Think of it as a walking, talking royal billboard for generations of intense inbreeding. But his challenges went way beyond just his appearance. His childhood was a marathon of medical issues and developmental delays. His skull bones hadn't even closed properly at 3 years old, and he couldn't stand until then or walk until he was 6. Even at 9, he struggled to get around. Imagine being king at 4, still exclusively breastfed and apparently biting his wet nurses and then being told to stop because it was in decor. Poor guy. He was plagued by constant illnesses. Measles, chickenpox, rubella, smallpox, basically every childhood disease you can think of. He had endless bronchial and dental infections and bouts of incurable diarrhea. And yes, he suffered from epileptic seizures, a condition we actually explored in detail when we talked about Emperor Ferdinand I, if you remember, which grew increasingly severe towards the end of his life. Intellectually, despite having the best tutors money could buy, he struggled immensely. At 9, he could barely speak, and reading or writing, forget about it. He lacked willpower and was easily swayed, though he did have frequent outbursts of anger. Essentially, he was physically and intellectually frail, leading to a reign marked by political instability and a struggling Castile. Then there was the elephant in the royal chambers, infertility. He was married twice, desperate for an heir, but it never happened. His first queen, Maria Luisa, even confided that he suffered from premature ejaculation, which when you dig into the research probably wasn't just about speed, but more about where the ejaculate was going, hinting at serious anatomical issues like hypospadias. And his later years were marked by severe physical decline, generalized edemas, swelling, extreme weakness, more fevers, and that persistent diarrhea. This constant state of infirmity, coupled with his inability to produce an heir, led the people and even Charles himself to believe he was bewitched. They actually tried exorcisms and weird potions like oil with exorcism blessings or eating powdered vipers. Yum! It truly shows how desperately they searched for an explanation for what to them seemed like a curse. So when he finally died in 1700, just shy of 39, the autopsy revealed some incredibly stark findings that perfectly explain his lifelong struggles and set the stage for our genetic decoding. A very small heart, corroded lungs, gangrenous intestines, 3 large kidney stones, a single testicle as black as coal, and wait for it, his head full of water. Oof. A condition called hydrocephalus, which we got into with Emperor Ferdinand I. That's the kind of complex, challenging life we're talking about. But now that we've set the scene, let's get down to the truly fascinating part. What genetic secrets were hiding behind all those symptoms? We're going to put on our genetic detective hats and investigate the leading theories that explain his lifelong struggle with developmental delays and intellectual disability, his probable intersexual state and infertility, why he had those mysterious skeletal deformities and the recurring infections, and ultimately his crucial kidney problems that led to his death. Get ready, because the puzzle pieces are about to click into place. All right, genetic detectives, remember those very awkward whispers right after Charles II was born? The ones hinting he might not be male, but female? Well, it turns out those whispers might have been onto something far more complicated than anyone in the 17th century could possibly have imagined. We're about to dive into the fascinating and often misunderstood world of disorders of sex development, or DSDs, specifically focusing on what's called true hermaphroditism, or as it's now more scientifically known, ovotesticular DSD, and also XX male syndrome. So what are we talking about here? In a nutshell, a person with true hermaphroditism has both ovarian tissue, which usually makes eggs, and testicular tissue, which usually makes sperm in their body. I know, wild, right? An XX male syndrome is another twist. It's where someone has the typical female chromosomes 46X but develops male characteristics. These conditions are rare, and they tell us just how complex our sex determination really is, far beyond just X and Y chromosomes. How does this even happen on a molecular level? Well, normally a tiny gene called SRY on the Y chromosome is the big boss, telling the body to develop testes. But in some cases of XX male syndrome, the SRY gene, being a bit of a rebel, actually translocates or jumps from the Y chromosome onto one of the X chromosomes during the dad's sperm formation. So even though the baby gets 2 X chromosomes, it also inherits this rogue SRY gene, which kicks off male development. Now it gets even more fascinating. In some cases of true hermaphroditism, or XX males, the SRY gene isn't even there. This points to other sneaky genes on the X chromosome, or other chromosomes, we call them autosomes, that can step in and mess with the sex-determining pathway. We're talking about genes like RSPO1 or PROCR2, which when mutated can lead to these complex DSDs. It's like a whole orchestra of genes trying to play the tune of boy or girl, and sometimes a few notes get played in the wrong order, creating a unique blended melody. For Charles II, this genetic soup could explain so much. Remember his single testicle as black as coal from the autopsy? That's our direct evidence of testicular abnormality, perhaps unilateral testicular agenesis or an atrophic cryptorchid testicle, and his queen's rather awkward confession about his premature ejaculation, where the poor ejaculate didn't enter her vaginal cavity. That strongly points to hypospadias, a condition where the urethra opens on the underside of the penis, which often accompanies ambiguous genitalia in DSDs. Combine that with his lifelong infertility and the rampant whispers about his sex at birth, and the picture becomes clearer. Charles II most probably lived with an intersexual state, likely true hermaphroditism or XX male syndrome. It perfectly explains why he couldn't fulfill his most crucial royal duty, producing an heir, and gives a powerful scientific explanation for what people thought was bewitchment. So while the court was busy with exorcisms, the real story was unfolding deep within Charles's chromosomes and genes. a complex testament to the power of genetics. But this is just one piece of his astonishing medical puzzle. All right, detectives, we've talked about Charles's very confusing plumbing, but let's shift our gaze to another major challenge he faced: his significant developmental delays and intellectual disability. Remember how he couldn't walk until he was 6 or speak properly at 9 and struggled immensely with learning? For centuries, people just thought he was slow or, again, bewitched. But modern genetics offers a much more precise suspect: Fragile X syndrome. So what exactly is Fragile X? Well, it's the most common inherited cause of intellectual disability, and it's a bit of a tricky one. It happens because of a peculiar genetic glitch on the X chromosome. Specifically in a gene called FMR1. Inside this gene, there's a small section where a DNA sequence CG gets repeated over and over and over again, too. If you get more than 200 of these repeats, it's like a genetic alarm going off. This massive expansion causes the FMR1 gene to effectively silence itself. It gets shut down through a process called hypermethylation. When the FMR1 gene goes silent, it can't produce a crucial protein called FMRP, Fragile X mental retardation protein. Think of FMRP as a really important messenger in your brain, helping to build and maintain healthy connections between neurons, especially at the synapses, those tiny gaps where brain cells communicate. Without FMRP, these connections get all wonky, leading to issues with learning, memory, and behavior. It's a bit like trying to build a superhighway for thoughts, but you're missing all the key construction workers. Now, how does this fit our king? Perfectly. Many of Charles II's documented symptoms align with FXS. His significant intellectual disability, his struggles with speech, dysarthria, and those marked developmental delays from early childhood are hallmarks. And remember those portraits we looked at? The research tells us that FXS often comes with a distinctive facial appearance: a long face, prominent chin and ears, and macrocephaly, a larger head in early development. These features, along with his documented joint slackness, muscular hypotonia, and difficulties walking, map strikingly well onto the typical FXS physical phenotype. Even his head full of water, which we mentioned from the autopsy, could connect here. Some individuals with FXS show enlargement of the brain's lateral ventricles, which are the fluid fill spaces, a potential link to that finding. And while FXS often comes with enlarged testes, macroorchidism, Charles had an atrophic one. But that's where the plot thickens with his other probable conditions like XX male syndrome, creating a really complex interplay. So while he wasn't bewitched by a sorcerer, Charles II's mind and body might have been profoundly shaped by this subtle yet powerful genetic fragility on his X chromosome, offering a truly scientific explanation for his lifelong struggles. And believe it or not, there's even more to this royal puzzle. So far, we've talked about the ambiguity of Charles II's sex development and his intellectual struggles, but now let's zero in on one of his most defining and tragic characteristics: his profound infertility. Remember that chilling autopsy finding of his single testicle as black as coal? That wasn't just a grim detail. It points directly to a major genetic suspect, Klinefelter syndrome, or KS. Klinefelter syndrome is actually the most common sex chromosome disorder in males. Instead of the typical 46Y chromosome set, individuals with classic KS have at least one extra X chromosome, most commonly a 47XY karyotype. It's like accidentally getting an extra instruction manual for one part of your development. Now, how does this extra X cause issues? While most of the genes on that extra X chromosome actually get silenced, a clever biological trick called X inactivation, a crucial few escape this silencing. These rogue genes now present in an extra copy can mess with the delicate balance of development, particularly male sexual development. For Charles II, if he had KS, it would likely have been a mosaic form, meaning some of his cells would be the typical 46XY and others would be 47XY. Why do we lean towards mosaicism for Charles? Well, classic KST often comes with features like unusual tallness and gynecomastia, enlarged breast tissue, neither of which Charles II was known for. So his historical presentation points away from the classic 47XY, but the mosaic version can explain his symptoms without those other common traits. And what symptoms are we talking about? The fit is almost uncanny. The most striking commonality is the small atrophic testes and the resulting infertility. This is practically the hallmark of KS. The extra X chromosome severely disrupts the development and function of the testes, leading to impaired sperm production and low testosterone, a condition known as hypergonadotropic hypogonadism. This perfectly aligns with Charles's documented sterility and that autopsy finding. Beyond the reproductive issues, KS can also contribute to the kind of cognitive and language deficits we saw in Charles. Individuals with KST often experience verbal and language difficulties, learning disabilities, and sometimes even social challenges. So his struggles with speech, writing, and overall intellectual development could very well have been compounded by this chromosomal anomaly. So while he didn't fit every textbook description of Klinefelter's syndrome, the mosaic form of chaos offers a compelling explanation for the core of Charles II's male reproductive failure and contributes significantly to his overall developmental struggles. It's another powerful piece of evidence suggesting that the bewitchment was actually a complex genetic inheritance playing out in real time. All right, genetic detectives, we've pieced together some fascinating parts of Charles II's genetic puzzle, from his ambiguous sex to his mental struggles. But what if there was one underlying genetic condition that could explain almost everything? One diagnosis that acts as a kind of master key to unlock this royal medical mystery. Well, some modern researchers are strongly suggesting a very strong candidate, aspartyl-glucosaminuria, or AGU. Now, AGU sounds like a mouthful, but let's break it down. It's a lossal storage disorder, and it's inherited in an autosomal recessive manner. What does that mean? It means you need 2 faulty copies of a specific gene, one from each parent, to get the disease. And if you've been listening to this podcast, you already know what that screams: inbreeding. This is why AGU, though rare worldwide, is much more prevalent in populations with a high degree of consanguinity, making the Habsburgs a prime suspect pool. So how does AGU work its molecular mischief? It's all about a tiny enzyme called aspartyl-glucosaminidase, or AGA, which is produced by the AGA gene on chromosome 4. This enzyme is like a cellular recycling worker, responsible for breaking down certain complex sugar protein molecules called inside your cells, recycling centers, the lysosomes. But in AGU, due to a mutation in the AGA gene, this enzyme is either deficient or completely missing. What happens then? It's like your recycling bin overflows. These gliosasparagens can't be broken down, so they accumulate and build up, especially in the brain and connective tissues. This toxic buildup essentially clogs up the cellular machinery, leading to progressive dysfunction in virtually all cell types over time, particularly neurons. And this is where Charles II slots in so perfectly. Remember his distinctive facial features, those we noted in his portraits. The research on AGU describes a very specific facial phenotype: widely spaced eyes, puffy eyelids, small ears, full lips, a square and prominent jaw, and a short, broad nose. Sound familiar? Many of these align directly with the famous Habsburg jaw and his overall appearance. Plus, AGU patients are often described as appearing prematurely aged, which certainly fits Charles's rapid decline in appearance. Beyond his looks, AGU explains so many of his other chronic issues: his early developmental delays, delayed speech and motor skills, his progressive intellectual disability, his skeletal abnormalities, and even his recurrent infections are all classic symptoms of AGU. Remember his clumsiness and walking difficulties. AGU can cause gait disturbances and muscular hypotonia. Even his epileptic seizures are a recognized feature of the syndrome. And that early macrocephaly that often progresses with AGU could even tie into his head full of water autopsy finding. The beauty of the AGU hypothesis is that it provides a single overarching genetic explanation for the full breadth of Charles II's ailments, from his physical appearance and intellectual struggles to his recurrent infections and ultimately his overall fragile health. It truly makes you wonder if the bewitched was simply a tragic case of faulty cellular recycling. All right, genetic detectives. We've explored some pretty intense internal genetic conditions so far, but what about the most famous, most visible sign of the Habsburgs' tangled family tree? We're talking, of course, about that legendary, unmistakable Habsburg jaw. In Charles II, it was particularly pronounced, literally jutting out in every portrait, making him look rather formidable, shall we say. Scientifically, this famous jawline is known as mandibular prognathism. It's a condition where the lower jaw protrudes significantly forward beyond the upper jaw, giving a prominent chin and often a concave facial profile. It wasn't unique to the Habsburgs, of course, but boy did they perfect it. So, how did this rather dramatic facial feature get so pronounced in the family and especially in Charles? Unlike some of the other complex syndromes we've discussed, the Habsburg jaw is often considered a multifactorial and polygenic trait. What does that mean? It means it's not usually caused by a single rogue gene, but by the combined effect of many genes working together, or in this case, perhaps a bit too enthusiastically. Genes like ADAM TSL1HN1 and CO2A1 have all been implicated. For example, mutations in ADAM SL1 can lead to a failure in properly regulating cartilage growth, causing the lower jaw to just keep growing a bit more than it should. And here's where the inbreeding comes back to haunt us. While some families might have a genetic predisposition to this jaw, the Habsburgs kept doubling down on it. By consistently marrying close relatives, they relentlessly concentrated these specific gene variants generation after generation. It's like selectively breeding for a very specific trait. Except in this case, it was a prominent chin and a severely misaligned bite. What dentists call a Class III malocclusion. For Charles II, this wasn't just a quirky family resemblance. His jaw was so severe, it famously made chewing incredibly difficult, leading to poor eating habits and likely contributing to his overall frailty. It probably even impacted his speech, dysarthria, making his already labored communication even more challenging. So that famous Habsburg jaw wasn't just a visual signature of his lineage, it was a daily struggle, a constant physical reminder of his family's genetic legacy. It's a stark visual testament to the cumulative effect of inbreeding, showing how specific traits can become amplified to debilitating levels. All right, genetic detectives. We've explored the genetic roots of Charles II's ambiguous sex, intellectual disabilities, and even his iconic jaw. But now, let's address the very organs that ultimately failed him, his kidneys. Remember that stark autopsy finding, 3 large kidney stones, and the fact that he suffered from incurable diarrhea and generalized edema swelling in his final years. These are all strong hints that his kidneys were in serious trouble. While we can't definitively say Charles II was born with only one kidney, congenital monorenal status, the autopsy only mentions a single testicle and the kidney stones. It's possible that the other kidney was either absent from birth or severely underdeveloped. A condition that falls under the umbrella of congenital anomalies of the kidney and urinary tract, CUT. CUT is a broad term for structural abnormalities that can arise during fetal development. What's the genetic connection? Well, CUT is incredibly complex with over 200 genes potentially involved. Some of the key players include genes like COL4A3, COIL4A4, COIL4A5, HNF1B, PKD1, and PKD2. Mutations in these genes can disrupt the delicate dance between the developing ureteric bud and the intermediate mesoderm, the tissues that form the kidney. This disruption can lead to a whole spectrum of problems from mild reflux to complete kidney agenesis absence. Even if Charles II did have 2 kidneys at birth, CUT can still be a factor. Many of these anomalies predispose individuals to chronic kidney failure (CKD) later in life. Why? Because the abnormal kidney structure often leads to reduced nephron number, the kidney's filtering units, and compensatory hyperfiltration. The remaining kidney works overtime to compensate. This extra workload can cause progressive damage over time. But what about those kidney stones? Well, kidney stones themselves aren't directly caused by CUT, but they are a common complication of CKD. The impaired kidney function can lead to an imbalance of minerals and other substances in the urine, making it easier for stones to form. And those stones, in turn, would have further damaged his already compromised kidneys. Incurable diarrhea and edema swelling in Charles's final years are also classic signs of advanced kidney failure. The kidneys are crucial for regulating fluid balance in the body, so when they fail, fluid can build up, causing swelling. And the diarrhea, well, that can be a complex symptom of uremia, the buildup of toxins in the blood when the kidneys can't filter properly. So, while we can't definitively say which specific genetic mutation or anomaly Charles might have had, the evidence strongly suggests that his kidneys were a major weak point in his already fragile health. It's a tragic culmination of his genetic inheritance, ultimately contributing to his early death. And there you have it, genetic detectives. We've journeyed through the tragic, complex, and utterly fascinating life of Charles II, the Bewitched. What his contemporaries saw as a dark curse, we've decoded through the lens of modern genetics, revealing a cascade of inherited conditions, from his likely intersexual state and fragile X syndrome to the broad impact of aspartate glucosamine, the subtle effects of Klinefelter syndrome, that iconic Habsburg jaw, and ultimately his failing kidneys. His story is a powerful, albeit heartbreaking, testament to the profound consequences of extreme inbreeding, and a vivid reminder that sometimes the biggest mysteries in history are just waiting for science to catch up. The story of hemophilia and European royalty is a compelling intersection of genetics and history, most notably linked to Queen Victoria of the United Kingdom. Born in 1819, Victoria's reign spanned a transformative era, but unbeknownst to her and her contemporaries, she carried a genetic secret that would ripple through the royal houses of Europe for generations. While Victoria herself was not affected by hemophilia, she was a carrier of the mutated gene on one of her X chromosomes. Understanding XL recessive inheritance is crucial here. As we now know, females have two X chromosomes. If one carries the mutated gene and the other is normal, the normal gene usually compensates, making her a carrier without symptoms. However, she has a 50% chance of passing on the mutated X chromosome to each of her children. It was through Victoria's descendants that hemophilia manifested in several prominent royal families. Let's trace this transmission. One of her sons, Prince Leopold, Duke of Albany, was affected by hemophilia. He experienced the debilitating symptoms of the disorder throughout his life. Two of Victoria's daughters, Princess Alice and Princess Beatrice, were carriers just like their mother. Princess Alice married Prince Louis IV of Hesse, and one of their daughters, Alexisandra, became Alexisandra Feodorovna, Alex of Hesse, upon her marriage to Tsar Nicholas II of Russia. This link introduced hemophilia into the Russian imperial family. Their only son Alexis, Tsarevich of Russia, inherited the mutated gene from his mother and suffered from severe hemophilia B. Princess Beatrice married Prince Henry of Battenberg, and one of their daughters, Victoria Eugenie, married King Alfonso of Spain, thus introducing hemophilia into the Spanish royal lineage. Several of their sons were affected by the disorder. The fact that hemophilia seemed to appear suddenly in Queen Victoria's descendants sparked much speculation at the time. While the exact origin of her mutation remains a subject of historical and genetic inquiry, it's understood that such spontaneous mutations can occur. The consequences of this genetic inheritance were far-reaching, extending beyond the personal suffering of those affected. In Russia, as we touched upon, the illness of Tsarevich Alexis had profound political implications. The chronic and unpredictable nature of Alexis' hemophilia created immense stress within the Romanov family. Their desperate attempts to manage his condition led them to seek the controversial counsel of Grigori Rasputin. Rasputin's influence gained through his perceived ability to alleviate Alexis' bleeding episodes further alienated the royal family from the Russian public and the aristocracy, contributing to the growing discontent that ultimately culminated in the 1917 revolution. It's a stark example of how a genetic disorder seemingly confined to the private lives of a family could have significant ramifications on the course of history. The vulnerability exposed by Alexis's illness, coupled with the perceived mismanagement and the influence of figures like Rasputin, weakened the monarchy at a time of immense social and political upheaval. Similarly, in Spain, the health of King Alfonso's sons affected succession and stability within the royal family. The public awareness of this royal disease also began to shape perceptions of the monarchy in other European nations, raising questions about lineage and fitness to rule. The dramatic historical saga of hemophilia in European royalty provides a compelling backdrop to understanding the fundamental biological processes at play. What was once a mysterious affliction, shaping the destinies of nations, is now understood through the lens of modern science. Hemophilia is fundamentally characterized by a deficiency in specific blood clotting factors, leading to an impaired ability to form stable blood clots and control bleeding. The the severity of symptoms is directly correlated with the level of the deficient clotting factor activity in the individual's blood. The primary clinical manifestation is prolonged and often excessive bleeding. This can occur spontaneously without any identifiable injury or as a result of trauma, surgery, or dental procedures. The nature and frequency of these bleeding episodes vary widely depending on the severity of the hemophilia. A hallmark of moderate to severe hemophilia is hemarthrosis, bleeding into the joints. The joints most commonly affected are the knees, elbows, and ankles. These bleeds can cause acute pain, swelling, and inflammation. Recurrent hemostasis leads to chronic joint damage known as hemophilic arthropathy, characterized by cartilage destruction, synovial thickening, and ultimately impaired joint function, pain, and stiffness significantly impacting mobility. Bleeding into muscles known as hematomas is also common. These can cause pain, swelling, and if large enough, may compress nerves and blood vessels, leading to further complications. More serious bleeding can occur in internal organs, including the gastrointestinal tract and the kidneys. Bleeding within the brain is a rare but life-threatening complication that requires immediate medical intervention. Bleeding in the neck or throat can also obstruct the airway and be life-threatening. Even minor injuries, such as superficial cuts or bruises, can result in more significant and prolonged bleeding in individuals with hemophilia compared to those with normal clotting function. Similarly, surgical and dental procedures pose a considerable risk of hemorrhage and require careful planning and management, often involving pre-treatment with clotting factor concentrates. The age of onset and the initial presentation of symptoms can vary. Severe hemophilia often manifests in early infancy with spontaneous bleeds or excessive bleeding following minor trauma, such as during circumcision or vaccinations. Milder forms of hemophilia may not be diagnosed until later in childhood or even adulthood, often following a significant injury or surgical procedure. It is crucial to distinguish between the two main types. Hemophilia A, caused by a deficiency in coagulation factor VIII, and hemophilia B, or Christmas disease, caused by a deficiency in coagulation factor IX. Clinically, the bleeding symptoms are very similar in both types, and laboratory testing is required to differentiate them by measuring the specific factor levels. As we discussed in the historical context, hemophilia A and B are inherited as XL recessive disorders. This means the genes responsible for producing the deficient clotting factors are located on the X chromosome. Hemophilia A, the more common form, is caused by mutations in the F8 gene, located on the long arm Q of the X chromosome at position XQ28. This gene spans approximately 186 kilobases and contains 26 exons. Mutations in the F8 gene lead to a deficiency in functional coagulation factor VIII. These mutations are highly diverse and can include inversions, particularly a common inversion involving intron 22 or intron 1 of the F8 gene, which accounts for a significant proportion of severe hemophilia A cases. Deletions and insertions ranging in size from small, affecting a few base pairs, to large, encompassing entire exons or the whole gene. Point mutations, including missense mutations, changing a single amino acid, nonsense mutations, introducing a premature stop codon, and splice site mutations affecting the processing of pmRNA. The type and location of the mutation in the F8 gene often correlate with the severity of hemophilia A. Mutations that result in a complete absence of FI protein or a severely truncated non-functional protein typically lead to severe hemophilia A. Mutations that allow for the production of some functional FVR read protein result in moderate or mild forms of the disease. Hemophilia B, the royal disease, is caused by mutations in the F9 gene located on the long arm Q of the X chromosome at position XQ1Q7.2. This gene is smaller than the F8 gene, spanning approximately 34 kilobases and containing 8 exons. Mutations in the F9 gene lead to a deficiency in functional coagulation factor IX. Similar to hemophilia A, the types of mutations in F9 are varied and include deletions and insertions affecting part or all of the gene, point mutations, including missense, nonsense, and splice site mutations, large rearrangements, although less common than the intron 22 inversion in F8. The specific mutation identified in the Romanoff family was a mutation in the F9 gene that disrupted RNA splicing, leading to a severe form of hemophilia B. The XL recessive inheritance pattern dictates how these genes are passed down. Males XY who inherit an X chromosome with a mutated F8 or F9 gene will have hemophilia because they have no corresponding normal allele on the Y chromosome. Females XX who inherit one mutated X chromosome are typically carriers. They usually have sufficient clotting factor produced from their normal X chromosome to prevent significant bleeding. However, they have a 50% chance of passing the mutated X chromosome to each of their children. For a female to manifest hemophilia, she generally needs to inherit a mutated gene on both of her X chromosomes, homozygous or compound heterozygous. This is a rare occurrence, more likely in situations of consanguinity, although, as we noted historically, this wasn't the primary driver in the European royal families. Other mechanisms for hemophilia in females include skewed X inactivation or chromosomal abnormalities involving the X chromosome. Carrier females can sometimes have lower than normal factor levels due to the random nature of X inactivation, where one of the two X chromosomes is silenced in each cell. If by chance a larger proportion of cells inactivate the normal X chromosome, the carrier female may exhibit mild bleeding symptoms. The story of hemophilia serves as a powerful reminder of the intersection between genetics and history, and how a single gene mutation can have profound and far-reaching consequences, shaping not only individual lives, but also the course of nations. Tonight, we're embarking on a journey to the land of pharaohs, a realm of immense power, breathtaking monuments, and enduring mysteries. So close your eyes and listen. For centuries, our understanding of these ancient rulers, their lives, their lineages, their very beings, has been shaped by the hieroglyphs they left behind, the majestic tombs they built, and the artifacts they were buried with. But what if we could delve deeper? What if we could unlock secrets hidden within their very bones, within the ancient echoes of their DNA? Let's talk about two specific genetic challenges that may have profoundly impacted the infamous King Tut's life: the mystery of his clubfoot and the possibility of a cleft palate. These aren't just minor historical footnotes. They speak volumes about the genetic lottery he lost, largely due to a family tree that curled back on itself like a pharaoh's sacred cobra. We're diving deep into the microscopic world of Tutankhamun's genes, exploring how inherited traits amplified by generations of extreme inbreeding left their undeniable mark on this iconic ruler. Let's start with something that literally shaped his walk through life: his clubfoot. Now, if you've ever seen images from Tut's tomb, you might notice something peculiar among his treasures: 130 walking sticks. Yes, you heard that right, 130. This wasn't just a pharaonic fashion statement. It was a glaring clue that our boy king had some serious mobility issues. And indeed, examinations of his mummy, particularly those fancy CT scans, have confirmed a significant deformity in his left foot, often described as a club foot. It's a common congenital condition where the foot is turned inward and downward, making walking, well, a bit of a heroic effort. So how does one end up with a club foot, genetically speaking? Turns out it's not usually just one grumpy gene throwing a tantrum. Clubfoot is a complex beast with both genetic and developmental roots. We're talking about a whole team of genes and pathways that need to work in perfect harmony during early limb development. Think of it like trying to assemble a really intricate Lego set. If even a few key instruction steps are missing or out of order, the final structure just won't quite fit together. Scientists have pointed to several genes that are often involved when things go wrong. We're talking about players like PX1, TBX4, and various Hox genes. These aren't just random letters. They're like orchestrators of limb formation, telling your leg and foot bones exactly how to grow and position themselves. If there's a mutation in one of these, or a combination of them, the foot can develop abnormally. It can also involve the very connective tissue and muscles we talked about earlier, giving us a whole tangled mess. And here's where Tut's family tree comes back into play big time. His parents were full siblings. Yes, you heard me right. This extreme inbreeding significantly upped the odds. Even if a specific clubfoot causing gene is rare or requires 2 copies recessive inheritance, keeping it in the family makes inheriting problematic combinations much more likely. It's like playing genetic roulette with a heavily loaded dice. So when we look at King Tut's foot combined with the bone necrosis or bone death due to poor blood supply that also affected it, those 130 walking sticks aren't just historical artifacts. They're poignant evidence of a young man battling a debilitating genetic legacy that literally shaped every step he took. It certainly paints a different picture than the golden boy on a chariot. So, we've walked a mile in King Tut's likely very uncomfortable shoes, understanding how his club foot and bone issues made every step a challenge. But now, let's move up to his face, to another congenital anomaly that some researchers suggest may have also impacted his life: a cleft palate. For those unfamiliar, a cleft palate isn't about having an extra palate for snacks, though that would be convenient. It's a birth defect where the roof of the mouth doesn't close completely during early fetal development, leaving an opening between the mouth and nasal cavity. This can cause issues with feeding, speech, and even recurrent ear infections. Now, a crucial point here, detectives. While Tut's clubfoot is pretty well evidenced by his remains in those 130 walking sticks, the cleft palate for him is a bit more of a whisper than a shout in the scientific community. Some interpretations of his CT scans and skeletal evidence suggest it, while others are less conclusive. However, given the overall picture of his health, and especially that family tree shaped like a pretzel, it remains a very strong and plausible hypothesis. So, genetically speaking, how does a cleft palate happen? Just like clubfoot, it's not usually the work of a single villainous gene. Cleft palate is typically multifactorial, meaning it's a complex tango between many genes, and sometimes even environmental factors. Imagine building a house and the genes are all the specialized contractors, the framers, the roofers, the plumbers. If too many of those contractors have faulty blueprints or are working a little sloppily thanks to genetic mutations, things might not align perfectly. Genes like GRHL3, FF6, CDH1, and many more are involved. These genes are crucial for guiding the delicate process of palate formation in the embryo, ensuring cells stick together properly and pathways signal correctly. If any of these get tangled, you can end up with a cleft. And what's the common thread here? You guessed it, that infamous inbreeding in Tut's family. When you're constantly marrying close relatives, you're not just concentrating the odds for one specific recessive condition. You're increasing the general genetic load. This means you're raising the chances of inheriting multiple subtle genetic variations that, when combined, can lead to complex developmental anomalies like a cleft palate. It's like rolling the genetic dice over and over again, and each time the odds of hitting a problematic combination just keep stacking up against you. So whether it was his foot or potentially his palate, these congenital anomalies paint a consistent picture. A young king born into immense power yet grappling with significant physical challenges from day one, all thanks to a complex and unfortunate genetic inheritance. It truly makes his short life all the more poignant. Seeing how the incredible power of ancient DNA analysis, basically historical CSI with mummies, pulled back the bandages, we found a young king battling a painful club foot, the likely burden of a cleft palate, and a body weak from multiple bouts of malaria. All thanks to a family tree that clearly needed some serious pruning and maybe a support group for its branches. Tut's story isn't just about a pharaoh's tragic curtain call. It's a loud and clear reminder that even with all the gold and power in the world, you can't outrun your genes. They really do write a heck of a story, proving that behind every grand title and golden mask, there was a real human being, often battling unseen genetic forces that even a pharaoh couldn't command. We've explored the genetic legacies that have shaped royal families. Now we turn our attention to a figure recently brought to vivid life on screen in Queen Charlotte. A Bridgerton story, King George III, the monarch who reigned over Great Britain during a pivotal era spanning the late 18th and early 19th centuries. As many viewers of the series will know, King George experienced periods of profound and unsettling illness, often referred to as the royal malady. These episodes of severe mental and physical distress were not just a personal tragedy for the king and his family. They also had significant political and social ramifications for the nation. For centuries, the true nature of King George III's ailment has been a subject of intense historical and medical debate. Numerous diagnoses have been proposed, ranging from psychological distress to physical ailments. Among the most compelling and enduring theories, particularly in the late 20th century, was the suggestion that the king suffered from a rare inherited disorder called porphyrias, affecting the body's ability to process hem. This theory gained traction based on retrospective analyses of his reported symptoms, which included episodes of abdominal pain, discolored urine, and marked neuropsychiatric disturbances, along with accounts of similar issues in some of his relatives. However, more recent and sophisticated analyses utilizing modern medical knowledge and even computer-based diagnostic tools have increasingly pointed towards a different explanation: bipolar disorder, also known as manic depressive illness. These studies argue that the cyclical nature of King George's manic episodes, his periods of apparent recovery, and his eventual cognitive decline align more closely with this psychiatric diagnosis. Today we'll delve into the historical context of King George III's royal malady and explore these competing theories. While current scientific consensus leans towards bipolar disorder, the Porphyrias hypothesis remains a significant part of the historical narrative. We'll then take a closer look at what porphyrias actually is, its genetic underpinnings, its biochemical pathways, and the array of symptoms it can cause, much like we did with hemophilia in our previous episode. Join me as we decode the complex health situation of King George III and the science behind the porphyrias theory. At its core, porphyrias refers to a collection of inherited or in some instances acquired metabolic disorders, stemming from defects in the heme biosynthetic pathway. Heme and iron-containing perforin's ring is a crucial component of numerous essential proteins, most notably hemoglobin in red blood cells, cytochromes involved in cellular respiration, and various other enzymes critical for life. The synthesis of heme is a meticulously orchestrated 8-step enzymatic process, each step under precise genetic control. In porphyrias, a deficiency or malfunction in any one of the genes encoding these enzymes leads to the pathological accumulation of specific hem precursors, perforin, or their biochemical predecessors in various tissues, including the liver, bone marrow, and arthritis. These accumulated intermediates are often toxic, giving rise to a diverse array of clinical manifestations. Historically, porphyria have captured the imagination, with some speculating their role in historical figures exhibiting unusual behaviors. However, our understanding today is firmly rooted in molecular genetics. The clinical spectrum of porphyria is remarkably broad, reflecting the specific gene mutation, the affected enzyme, the site of precursor accumulation, and the nature of the accumulated compounds. We broadly categorize porphyria based on their primary site of metabolic dysfunction: hepatic porphyria, where the liver is the main site of precursor overproduction, and erythropoietic porphyria, where the bone marrow and red blood cells are primarily affected. Hepatic porphyria often manifest with acute, potentially life-threatening attacks, characterized by severe abdominal pain, frequently described as colicky and poorly localized. These attacks can be accompanied by gastrointestinal disturbances such as nausea, vomiting, and constipation. Critically, many acute hepatic porphyrias also involve the nervous system, leading to a range of neurological symptoms, including peripheral neuropathy, muscle weakness, pain and sensory changes, seizures, and even encephalopathy with confusion, hallucinations, and altered mental status. Autonomic nervous system dysfunction can result in tachycardia, hypertension, and bladder dysfunction. In contrast, erythropoietic porphyria primarily present with cutaneous photosensitivity. Exposure to sunlight, particularly in the visible light spectrum, can cause painful non-blistering skin reactions, itching, swelling, and chronic skin changes. Some erythropoietic porphyria can also lead to anemia and splenomegaly. It's important to note that some porphyria types can exhibit a combination of both acute neurovisceral and cutaneous symptoms. The variability in clinical presentation underscores the complexity of these disorders and the need for careful diagnostic evaluation, often guided by genetic insights. The vast majority of porphyrias have a strong genetic basis resulting from inherited mutations in the genes encoding the 8 enzymes of the hem biosynthetic pathway. ALS1 gene is located on chromosomal loci 17q21.33. This gene primarily functions in the liver and other non-erythroid tissues. ALAD is located on chromosome 9q34. This gene encodes a cytosolic enzyme expressed in all tissues. HMBS, also known as PBGD, is located on chromosome 11q23.3. This gene encodes a cytosolic enzyme expressed in all tissues with erythroid-specific and non-erythroid-specific promoters. Next one is UROS, located on chromosome 10. This gene encodes a cytosolic enzyme expressed in all tissues. UROD, located on chromosome 1p34.1. This gene encodes a cytosolic enzyme expressed in all tissues. CPOX, located on chromosome 3q12.1q2.2. This gene encodes a mitochondrial enzyme expressed in all tissues. PPOX, located on chromosome 1q233 to q24.1. This gene encodes a mitochondrial enzyme expressed in all tissues. Fetch-ferrochelatase, located on chromosome 18q21.3. This gene encodes a mitochondrial enzyme expressed in all tissues with higher levels in erythroid cells. ALAS2, located on chromosome XP11.21. This gene is specifically expressed in erythroid cells. Over 1,000 different mutations have been identified across these genes, contributing to the significant molecular heterogeneity observed in porphyria and the wide spectrum of clinical presentations. These mutations, ranging from single nucleotide polymorphism SNPs, leading to missense or nonsense codons, to insertions, deletions, and splice site alterations, each affect enzyme activity and expression to varying degrees. Understanding the specific genetic defect and its location on the genome is paramount for accurate diagnosis and predicting inheritance patterns. Ongoing research is crucial to differentiate between truly pathogenic variants and benign genetic polymorphisms, refining our diagnostic accuracy and informing genetic counseling. The inheritance patterns of porphyrias vary, reflecting the nature of the mutated gene and its chromosomal location. The acute hepatic porphyria, namely acute intermittent porphyrias, AIP, due to mutations in HMBBS 11q3 hereditary, HCP due to mutations in CPOX 3q12.2, and variegate porphyrias VP due to mutations in PPOX 1q23 q224.1, are typically inherited in an autosomal dominant manner. This means that a single copy of the mutated allele from one parent is usually sufficient to predispose an individual to the condition. However, these conditions often exhibit low penetrance, meaning that not all individuals carrying the pathogenic genotype will develop clinical symptoms. The reasons for this variable expressivity and penetrance are complex and likely involve modifier genes and environmental factors. Rarer, more severe homozygous dominant forms where an individual inherits two copies of a severely mutated allele can also occur. In contrast, some porphyrias, such as ALA dehydrase deficiency porphyrias, ADP due to mutations in ALA 9q34, congenital erythropoietic porphyrias, CE due to mutations in UROS 10q26.3, and erythropoietic protophyria EP due to mutations in FH1 1820.3, follow an autosomal recessive inheritance pattern. In these cases, an individual must inherit two copies of the mutated allele, one from each parent, to manifest the disease. These conditions often present with more severe phenotypes due to the complete or near-complete loss of functional enzyme activity. There are exceptions to these typical Mendelian patterns. X-linked protoporphyria. XLP, a subtype of erythropoietic protoporphyria, is caused by gain-of-function mutations in the ALS2 gene located on the X chromosome, XP11.2121. This leads to increased activity of erythroid-specific ALA synthesis. Furthermore, Porphyria cutane tarda PCT, the most common porphyrias, demonstrates complex genetics. While there are familiar forms with inherited mutations in the UROD gene 1p34.1, autosomal dominant with low penetrance, the sporadic form is more prevalent and involves a combination of genetic predisposition, often a UROD polymorphism, and acquired factors such as iron overload and hepatitis C infection. Understanding the precise genetic defect and inheritance pattern through molecular genetic testing is crucial for accurate diagnosis, genetic counseling, and risk assessment for family members, allowing for informed reproductive decisions and potential preventative. As our exploration of porphyria on Decoding Dynasty draws to a close, we've uncovered the intricate genetic and biochemical disruptions in the vital hem synthesis pathway, tracing them to specific locations within our genome. These genetic variations can lead to a wide spectrum of symptoms, highlighting the power of our genes in shaping our health. It's fascinating to consider historical figures like King George III, whose perplexing episode sparked centuries of speculation with porphyria emerging as a potential explanation. This historical link underscores the long and often mysterious history of these genetic metabolic diseases. Today, thanks to advances in genetics and molecular biology, we are moving beyond historical enigmas. Precise genetic diagnoses and innovative treatments such as RNA interference are offering new hope for individuals living with porphyria. Continued research and increasing awareness promise a brighter future for those affected. Now let's tackle a mystery that spans millennia and continents, linking some of history's most head-scratching figures. I'm talking about King Tut, the ancient Egyptian pharaoh, whose looks were, shall we say, unique for the time. Then there's Niccolo Paganini, the violin virtuoso, so impossibly bendy and brilliant, people swore he'd made a deal with the devil. And swinging over to American history, the towering figure of Abraham Lincoln, a man whose gangly frame was as iconic as his top hat. What in the historical genetic heck could possibly connect this ancient boy king, a demonic fiddler, and a legendary president? Did they share a secret handshake, a favorite brand of ancient cereal? Nope. The whispers from the past, often backed by modern scientific squiggles on a chart, a fat point to something far more intricate, a sneaky little genetic condition that literally stretches the limits of the human body. Now, before we get too carried away with our genetic detective hats, a quick disclaimer, dear listeners, there's no definitive genetic proof that these three historical VIPs actually had this particular condition. For now, it's mostly a very educated guess based on their historical descriptions and peculiar physiques. But hey, that's half the fun, right? Because even if it's just a strong maybe, understanding this disease helps us interpret their lives and legacies in a whole new way. So we are diving into the world of Marfan syndrome, a disorder of the body's connective tissue. It's a syndrome that might just explain Paganini's unholy flexibility, Lincoln's famous stature, and even some of the more unusual depictions of our pharaohs. And we'll learn all about, if they had it, what exactly that would have meant for their bodies and their lives. So, buckle up, because we're about to untangle some very long limbs and even longer historical debates. Prepare to have your mind stretched as far as a Marfan limb as we decode this truly fascinating dynasty. So what exactly is Marfan syndrome? This genetic troublemaker that might link our seemingly desperate historical figures. Well, at its heart, quite literally, as we'll soon see, Marfan syndrome is a genetic disorder of connective tissue. Think of connective tissue as the body's superglue, its internal scaffolding. It's stretchy elastic bands holding everything in place. Bones, muscles, blood vessels, organs, even the lenses of your eyes. Now, if you have Marfan syndrome, this superglue isn't quite as super as it should be. The culprit is a tiny little mutation in a gene called FBN1. That's FBN1 for our science nerds out there, located on chromosome 15. This FBN1 gene gives instructions for making a crucial protein called fibrillin-1. Fibrillin-1 is the star player in building thread-like structures called microfibrils, which then go on to form the strong, flexible fibers of your connective tissue. Imagine building a magnificent elastic bridge. Fibrillin-1 is like the special super strong steel cables that give the bridge its flexibility and resilience. If those cables are faulty or there aren't enough of them because of a wonky FBN1 gene, the bridge might be built, but it's going to be a bit wobbly, prone to stretching too far, and maybe even some critical components breaking down over time. That's essentially what happens in a body with Marfan syndrome. What's really fascinating and a bit cheeky about Marfan is that it's usually inherited in an autosomal dominant pattern. This means you only need one wonky copy of the FBN1 gene from one parent to get the syndrome. So if a parent has Marfan, there's a 50-50 chance their child will too. And in about 25% of cases, it's a brand new mutation, a genetic oopsie that just happens spontaneously. Because connective tissue is everywhere in your body, Marfan syndrome can manifest in a whole spectrum of ways, with symptoms ranging from barely noticeable to life-threatening. This is super important because it explains why two people with Marfan might look and feel very different. We call this variable expression. Genetics loves to keep us on our toes. But generally, people with Marfan syndrome tend to share some common themes. You'll often see skeletal stretchiness. Think tall and slender builds, disproportionately long arms, legs, and fingers. Sometimes called arachnodactyly, which literally means spider fingers. Cool, right? They might also have really flexible joints, a curved spine, scoliosis, or a chest bone that either sticks out or caves in. Their face can also be long and narrow with a high arched palate. Ocular oddities. Eye problems are common. The lens of the eye, which helps you focus, can actually slip out of place because the connective tissue holding it is weak. Extreme nearsightedness is also frequent. Cardiovascular concerns. And this is the big one, the heavy hitter, the one that can be truly life-threatening. The aorta, that massive main artery carrying blood from your heart, relies heavily on fibrillin 1 for its strength and elasticity. In Marfan, it can weaken, stretch, and bulge an aneurysm or even tear a dissection. This is the reason why Marfan syndrome was historically a much more dangerous condition before modern medicine stepped in. So when we look at our historical figures, we'll be trying to spot these Marfan clues, those long limbs, the flexible joints, the specific facial features, and any historical accounts of heart or eye issues. Though, as you brilliantly pointed out, dear detective, the lack of definitive genetic evidence means these are fascinating hypotheses, not confirmed diagnosis, especially when that crucial heart problem isn't explicitly there. So, there you have it, detectives, Marfan syndrome. It's a genetic blueprint gone a little stretchy, potentially leading to some very distinct features, and most critically affecting that vital superglue throughout the body. We now know what to look for, and the delicate dance of genetics that makes every case a little different. But how do these genetic puzzle pieces fit our historical giants? Is Paganini's flexibility truly a symptom? Did Lincoln's height hide a genetic secret? And what about the pharaohs? Was Marfan just a royal red herring? We have now reached the end of our journey through the history of the Crimson Code. From the ancient sands of Egypt to the tragic thrones of Europe, we have seen time and again that no wealth, no power, and no crown can protect an individual from the intricate laws of biology. The stories of these kings, queens, and pharaohs are not just historical footnotes. They are powerful human reminders of the shared molecular thread that connects us all. Thank you for choosing this space for deep listening, study, or rest. We hope these genetic secrets provided the calming, engaging background you needed. Until our next scientific exploration, please continue to support the geneticist and sleep well. Good night.